Good day. I'm Norman Wildberger. Today we're going to look at graphing polynomials. This is a way of associating a visual geometrical object with what's up till now a purely algebraic object. Once we do that, we can interpret the tangents that we defined last time, the various kth tangents of a polynumber, first tangent, second tangent, third tangent, and so on. We can interpret those geometrically as tangent lines, tangent conics, which are approximating the polynomial at a point. Now I'm going to increasingly be using the polynomial word rather than the polynumber word to make contact with more classical mathematics. But I hope you keep in mind that for us a polynomial is just another word for a polynumber. So when it comes down to it, a polynomial like this is essentially just a list of numbers. The lists of the coefficients of the various powers of alpha. And today we're going to be talking about just those polynomials with integer coefficients, so-called integral polynomials or integral polynumbers. So our idea of representing such a polynomial graphically is to plot the values of pairs, numbers, and the polynomial's values at those numbers. That way we get a two-dimensional representation that somehow incorporates or allows us to visualize the polynomial. So let's start off by having a look at this particular polynomial and calculating some of these values of the polynomial at various constants. So here on the left-hand side I've listed various integers from -5 up till 10, and I've computed for you the values of this polynomial at the various constants. So this minus 166 here means that if you replace alpha with -3, then this evaluates to minus 166. So our idea is to graph pairs of such numbers in a two-dimensional setting. And for that we're going to go back to Cartesian coordinates. So this is a way of introducing geometry in a very concrete and explicit way, using essentially a sheet of graph paper with equally spaced horizontal and vertical lines forming this pattern of unit cells or squares. We can write a distinguished horizontal line and call it the x-axis, usual convention, and we can distinguish a particular vertical line and call it the y-axis. And we can label these various nodes here, 0, 1, 2, 3, 4, and so on in that direction, -1, -2, -3, and so on in this direction, and going up 1, 2, 3, 4, going down -1, -2, -3, and so on. And then the idea is that if we have a point like this one here, then we can look at the x coordinate, which is 1, and we can look at the y coordinate, which is 6, and then we can essentially give this point a name by associating it to the pair 1, 6 enclosed in square brackets by convention. So we can define a mathematical object called an integer point, which is just a pair of integers enclosed in square brackets. And it's an ordered pair, so there's a first one and a second one corresponding to the x coordinate and the y coordinate. That defines a new type of object, which we might call int squared, an integer point. And then a variant on that is when we do exactly the same thing, but we allow the numbers in the brackets to be rational numbers. In that case, we get a rational point, and this new type of object we can call a rat squared, or for simplicity, just a point. So a point is generally just a pair of rational numbers. So there's a point 1, 6, there's a point 0, 3, there's -1, 0, there's -2, -3. And we could also have talked about points which are not necessarily on the intersections, but sort of in other more random positions. Now, one of the lovely things about this Cartesian coordinate system, essentially introduced around the time of Descartes, is that we can encode lines and other nice curves like conics pleasantly in an algebraic form. So for example, this line here, which goes through these various points, so equally spaced 1 over 3 up, 1 over 3 up, 1 over 3 up, so this really is a line. This line can be described by the relation between the x and the y coordinates of the points on it. So the usual kind of description is in terms of an equation that we can write like this. In this case, 3x minus y plus 3 equals 0. Every point on this line happens to satisfy this equation. So for example, 1, 6, if you replace x with 1 and y with 6, then you get 3 minus 6 plus 3, which is indeed 0. So this point satisfies the equation, telling us this point is on the line. And you can check that all these points lie on the line in the sense of satisfying the equation. Now the x and the y are in some sense arbitrary. They're not really necessary. The essential ingredients are the various coefficients that appear here, and we like to abbreviate them by just talking about their proportion. 3 to minus 1 to 3. That encodes the line just as well as that does. And the pointy brackets sort of alerting us to the fact that we're talking about a Euclidean line. So we can talk about lines, and we can talk about points in this Cartesian coordinate system. Now maybe it's useful to say here that the algebraic side of things, when we're talking about points like this or points like this and lines like this, don't actually require a picture. The picture is a physical object, which is strictly speaking outside the world of mathematics. It resides here in the physical world in which we live. We're making various assumptions when we work with a picture like this. And we're also disregarding certain subtleties. For example, we're not fussing about exactly how wide these lines are. We're not fussing too much about exactly how big the points are that we're drawing. We're also kind of assuming that it is possible, in fact, to create a pattern like this where these lines actually are all equally spaced, and by implication where they're all parallel. So even if we were to extend these lines indefinitely, they would not meet. It's our idea of parallel. Same for the vertical lines. But that's really an assumption about the world in which we live in, which may or may not be completely true. It's a kind of an important point, so let me just say a little bit more about that. Imagine for a second that we're living on a round planet. Well, okay, we are. But imagine that this round planet was completely smooth and didn't have any objects on it, other than perhaps ourselves. Otherwise, it was a completely smooth, featureless Earth. For example, perhaps something like this. So imagine this is a model of the Earth, and perhaps you and I are right there. We're very, very tiny, so that as we look at the Earth, it's locally quite flat, and we see what looks to us like a plane. Now suppose that we attempted on this surface to draw such a grid plane. That would be a natural thing to do. We might make some strings and try to make some parallel lines, okay? And then some ones which are perpendicular, parallel lines like this. Okay? But if we started examining the geometry of this grid plane that we're making on the surface of the sphere, we would discover that it differs from this one subtly in measurable ways. In other words, the lines that we are, for example, thinking are parallel, if we actually extended them, we would find very likely that they meet. Or we would find that these two lines are perpendicular to this one. But if we move this line up and say to that one there, then these two lines are no longer perpendicular to it, which is quite different from our assumptions about this thing in the Euclidean plane. So in other words, there are assumptions about the physical world built into a model of this graph paper that we have in our booklets. It's not entirely obvious that a piece of graph paper exists. Well, yes, of course, it looks like it exists in your notebook, but if you made a very, very careful measurement of the various relationships between these lines and the various perpendicularities, you might find that the curvature of the universe somehow makes them not as perfectly aligned as we think they are. There's a bit of a can of worms that we have to recognize that we don't really know the true geometry of the world in which we live in. And since the 20th century, Einstein has taught us that the geometry of the world in which we live in is in fact much more complicated than we used to think it is. There is such a thing as curvature, and the true overall structure is far from settled. But in particular, it's probably pretty obvious that it's not completely Euclidean and straightforward the way people used to think 100 or 200 years ago. So we have to separate in our minds the mathematical model that we're working with, the theory that we're developing, and these pictures that we're drawing to help us visualize the mathematics. This is an important point, that for us, the expressions that we will write down will be primary. Logically, they take precedence. These pictures are just for us aids in understanding things. And we must be careful not to too quickly draw mathematical conclusions from the pictures that we draw. It's something to be aware of, a potential difficulty with relying too much on pictures. So this is the point I've just made, that the physical existence of a sheet of graph paper is separate from the mathematical model of integer points or rational points that we can work with algebraically. And there are empirical questions or technological issues associated with the graph paper and constructions in it. For example, is a sheet of graph paper really Euclidean? That's the issue we've already talked about. Do we live in a curved world? How does that affect the actual properties of a piece of graph paper? Another question is, can we extend such a sheet of graph paper? In many of our constructions, we might be interested in extending the axes perhaps quite a long ways to deal with very big numbers or very small negative numbers. So a natural question is, well, to what extent can we extend this graph paper? Obviously, there are physical barriers because we're living on a planet Earth of only a certain size, and of course in practice it's hard to get a piece of paper that's too big. But even theoretically, the large-scale structure of the universe may actually be kind of closed. There may not be room, even theoretically, in the universe to have a sheet of graph paper that, for example, extends indefinitely. Another sort of related or inverse question or issue to that one is, can we subdivide a sheet of graph paper arbitrarily? Suppose we want to create a finer mesh by, say, subdividing each of our squares into 10 little pieces. And then we want a yet finer one where we subdivide even those smaller squares into 10 little pieces and so on. Can we keep doing that? Well, theoretically we can, but in practice, empirically, in the world in which we live in, once we get down to very small scales, the laws of physics start becoming quite strange, and we arrive at limitations of our ability to resolve quantities, and quantum effects start interfering with our measurement. So in the real world, you can't keep subdividing things. Or to put it another way, when you subdivide things, things change. The laws of physics start changing on you, and you enter a world which is quite different from the way it is in our experience. So there actually are quite deep questions of a physical nature, the physical nature of the continuum or the large-scale structure of the universe, connected with a sheet of graph paper and what we actually can do with it practically. So one way of dealing with these issues is to say, all right, we're going to think of these graphs that we're going to draw and the pictures that we make as simply aids to our understanding. And that we're going to draw a line between the logic of what we're doing algebraically and the pictures that we're going to draw to help us understand things and maybe guide our intuition. because we are actually very visual creatures. We have a lot of brain processing devoted to visuals. So it makes sense to use that. It's one of our strengths. So let's go back to our polynomial, this one here, and let's try to graph it. Here are these various values that we've already computed. So here are now the pairs of numbers that we would like to graph. These are sort of integer points, and there's a range of them. And one thing that we see is that the y-coordinates, the second coordinates, are actually, well, they get quite big, especially big negative. So if we're going to hope to picture them, we should scale our grid in a rather different way than what we did before. And we have to allow ourselves this flexibility to scale the two axes in different ways. So here the x-axis has been scaled, so this is 1 unit. 1, 2, 3, 4, 5, 6, and so on. However, the y-axis has been scaled dramatically different. This now represents 100. So 100, 200, 300, 400, 500, that's 1,000. That's minus 500. That's minus 1,000. Now I haven't drawn all the lines because to do so would require thousands of lines. Okay, so we're going to adopt the convention that we're going to forget about all the lines, horizontal and vertical, except for the two axes themselves, and we're just going to use sort of parallel lines to locate the positions of points. So let's graph these points. Minus 5, minus 1,092. So minus 5 and then minus 1,092 is about there. And then this point, minus 4, minus 484, about there. Minus 3, minus 166, minus 2, minus 30, minus 18, 0, 8. Actually has the same y value. 1, 6, going down just a little bit. 2, 14, up a little bit. 3, 20, up a little bit more. Then down 4 to minus 12. 5, minus 142. 6, minus 454. And 7, minus 1,056. So these various points that we've drawn now are, in some sense, a picture of this polynomial. Now you might not be used to that kind of picture. You might be used to a more continuous picture. But if we're working over the integers, which we can suppose we're at least initially doing, then this is a very reasonable picture. Because in our minds, there are only integers. And we're just plotting various integer points. Of course, we're not plotting a lot of integer points. We're not plotting any of those points with the x-coordinate more than 6 or the y-coordinate less than 6. So in fact, this is just some very small fraction of a much bigger picture that we could extend far in either direction if we had the patience and the room to do so, and maybe also the computing power, because perhaps it would get quite involved to compute these things if the x's become very big or very big negative. So this is a graph. It's not the only graph that we can draw. It's a kind of a partial graph. It only encodes part of the picture. But nevertheless, it's some kind of physical representation that we can look at and say, there's some kind of pattern here. It's almost just like some dynamical thing moving. We might say it's an integral graph because all the points that we're plotting have integer coordinates. But a lot of times we are interested in not just integral values, but also rational values. In other words, points with rational coordinates. So let's say a few words about them. Suppose, for example, that we're interested in the standard grid plane here, where now the x-axis is here, the y-axis is here. And suppose we're interested in, say, plotting a point like this with rational coordinates. 9/2 and 5/3. 9 over 2, 5 over 3. Well, one way to do that is to say 9 over 2 is exactly halfway between 4 and 5, so we'll draw some point halfway between 4 and 5. And 5/3 is, well, somewhere between 1 and 2, and we'll do it roughly. But we would like to do it exactly because we would like to be completely correct here. So how do we construct such a point? It's important to realize that we can construct such a point with just lines connecting existing points in our grid plane. So I'm going to show you how to do it for this point, and I hope you'll see the pattern. To get 9/2, first of all, on the x-axis here, what I'm going to do is I'm going to consider a rectangle, this one right here, which is 9/, and 2 up. So that point there is the point with coordinates 9, 2. And I'm going to connect that point to the origin with this green line. Now where that green line crosses the line x equals 1, because this is exactly halfway, this will be exactly halfway there. So this will be the coordinate 4.5, or 9/2. In a similar way, if we want to get 5/3 in this direction, what I do is I make a rectangle that goes 5 this way and 3 this way. So this rectangle right here, this is the point with y coordinate 5 and x coordinate 3. I draw the line connecting the origin, and I see where that line meets the line x equals 1 now, in that point there. So what is the y coordinate? Well, this is 1/3 of the way from here to here. That's 1/3 of the way. And so this will be 1/3 of the way to here. So that point there will be 5/3. And all what we've needed to do that is to connect points that are already in the grid plane. To create that line, and to create that line, and see where those two lines cross lines that are part of the grid plane. So once, of course, we have the x coordinate here and the y coordinate here, it's not too hard to make parallel lines, which then give us the required point. So with this technique in hand, we can now extend our view of a polynomial. We can now say, all right, let's try to visualize a polynomial p by plotting many points of the form c, p of c, where c now are suitably chosen rational numbers in a certain chosen range. In other words, we don't have to stick with integer values of c. We can substitute more general rational values and plot those points. So now let's have another look at our favorite polynomial, this one right here. The existing points that we have already drawn, the ones with integer values in this range, are right there. Now I'm going to add some new points, the green ones, whose x coordinates are half, minus a half, 3/2, minus 3/2. In other words, sort of halfway between the various points that we already have. So if I plug in 1/2 into here and compute, I get 95/16. And when I plot that, there's the x coordinate 1/2. 95/16, that's roughly about 6. And so with those two coordinates, we can plot that point there. There it is there right in the green. And I've also plotted minus a half, 159/16, 3/2, and 143/16, minus 3/2, and minus 49/16, 5/2, which is there, and 303/16, minus 5/2, and minus this. No, that's out of our range, so I wasn't able to graph that one. 7/2, that's 3.5, that's this one over here with 191/16, and 9/2, and minus 961/16, that's just barely in our range. So we have these new green points now to augment the red ones that we already have. And now, because I'm interested in a rational graph, what I'm going to do is I'm going to do a time-honored technique that goes back to primary school, or probably even earlier. We are going to join the dots. We're going to take our ruler, or our straight edge, and just join these adjacent points, because they're all one after the other in a certain order. join them up with this black line, just straight line segments from one to the next, and then we get some kind of picture of a part of the polynomial. Of course, this is not a complete picture. It's not complete for two different opposing reasons. It's important to appreciate both of these ways in which this is not complete. It's not complete, first of all, because we only went from here to here. All the values to the right here, all the values to the left here, were not included in the picture. We could have included some more of them by making the paper larger, or perhaps by scaling our axes appropriately. But no matter how we do that, no matter how big a piece of paper we have, no matter how much we scale, we still only get always a finite part of a bigger picture. It's always possible to extend the picture, so we never get the whole picture this way. There's another way in which we don't get the whole picture because we've only subdivided each one of these intervals into, in this case, two pieces. Now I could come along and say, well, I'm going to do a better job. I'm going to subdivide each one of these intervals into, say, 10 pieces. So I could calculate 10 different values and plot them all. Then I would get a much finer resolution, but still, it would only be a partial picture. There's still a resolution in here, and between the points that I'm plotting, I'm not really getting the accurate values. I'm replacing the values with straight line segments. Actually, if you have a computer program that plots curves like this, it might even dispense entirely with drawing little line segments if the number of points is sufficiently large. If I divided each one of these pieces into, say, 100 and plotted all the points, then those points would probably run together, forming what looks to you like a continuous curve. There'd be no need to make a little adjoining lines. So in fact, mathematics programs that do make calculations do almost exactly this. They use a join the dots method, or they just deal with dots themselves. Sort of a pixel approach, or like a vector graphics approach. But the important thing to realize is that even if the picture that your computer is outputting looks very smooth, it's an illusion. It is not the real picture. It is a picture that has been derived by going to a certain resolution and no further. Just the way it is. It's just as impossible to plot all the points in one of these little intervals as it is impossible to plot all the points on the whole line, whatever those terms even mean. We can go a certain ways in both directions, and that's just the natural limitations of this mathematical problem. So this picture here that I'm drawing here is actually very representative of what actually happens in practice. And there's no need to be ashamed of drawing straight line segments. That way we stick with something that's completely concrete. I could have tried to sort of artistically draw a curve through there, but that would be a bit sloppy because I would probably not do a very good job, and also if I did it again the next day, the curve that I drew would be probably noticeably different from the curve I drew today. So it's not really reproducible, and it's also very difficult to specify to you what exactly I have done. Sorry from taking a picture. But here you can specify this and pass the instructions over the internet to someone else, and they can create more or less the same diagram, subject to the actual widths of points and widths of lines that you're going to use. So this is the essence of plotting polynomials. Now let's turn our hand to some interesting applications involving tangents. At the end of last lecture, I gave you an exercise to do, which I strongly encouraged you to do, which was to calculate various tangents to this cubic polynomial. 5 minus 3 alpha minus 4 alpha squared plus alpha cubed. So let's have a look at some of those tangents, and you can compare with with what I've got, see if I've gotten the right answer. And I'm also going to graph not just the original cubic, but also various tangents. The original cubic, P, is plotted here. So this sort of signifies the coding, the red points and the black lines. I'm just using integer points here, so you can think of this, if you like, as being essentially over the integers. Integral points, and I'm joining the dots between these integral points, and beyond these ranges, the numbers go off my scale, which goes roughly from 20 to minus 20, or maybe down to minus 30. Okay, let's consider the various tangents to this at the point 0. Those are the simplest to read off because they just correspond to truncating this expression in various ways. The simplest truncation is when we ignore all of those things and we just get the 0th tangent at 0, which is just 5. Well, that's also a polynumber or polynomial, and we can plot it also. It's very simple to plot. It just turns out to be this line. Why? Because we're plotting all the points of the form C and this thing evaluated at C. But this thing evaluated at C is always 5. So we're plotting 1, 5, 2, 5, 3, 5, 4, 5, and so on. All of the points just along this line where the y-coordinate is 5. So there's the 0th tangent to this cubic at the point 0. The first tangent is what we get when we disregard everything except the constant and the linear terms. That's 5 minus 3 alpha. That's a linear polynomial. And what does that look like? Well, it looks like this line right here with the blue dots and the red line. It is a line. It's the line y equals 5 minus 3x, if you like to think in terms of x and y. So for example, when x is 0, then we get the value 5. When x is 1, or alpha is 1, we get the value 2. When alpha is 2, we get the value minus 1, and so on. The second tangent to the polynomial at 0 is what we get when we just drop that cubic term. So it's 5 minus 3 alpha minus 4 alpha squared. And we can plot that also for different values, minus 1, 0, minus 2, and so on. We can plug it into here and get the corresponding y-coordinate. And I've graphed them for you. So there's this point here, this one, this one, this one, this one, and this one. Those are the values that are graphable in the range that I've drawn. So to summarize, the original cubic is pictured by these points. The 0th tangent is plotted by these points, or that sort of horizontal line. The first tangent, or the tangent line, is plotted by these points. And the second tangent line, or the tangent conic, at 0 is represented or graphed by those points. So you can see that this is a purely integral graph. This is a picture that you could draw even if you did not know what fractions were. If you only knew arithmetic with integers, you could draw this picture. And you can see some shape. You can see some shape and some patterns even though we're only working over the integers. Now let's have a look at the same curve, but from the point of view of a different point. Not 0, but we'll choose another point, let's say the point 2, and see what the various tangents to the same curve look like at the point 2. In other words, sort of at this point here. So the tangents at 2, I asked you to compute last time. And it turns out that the 0th tangent at 2 is the constant minus 9. The first tangent at 2 is 5 minus 7 alpha. and the second tangent at 2 is 13 minus 15 alpha plus 2 alpha squared. And I've plotted those for you. Minus 9, that's the horizontal line consisting of these green points. The tangent line, 5 minus 7 alpha, is that line there, consisting of these points. And the tangent conic is, well, it has quite a different shape in this case. It's kind of a parabolic thing opening upwards now. It's still touching there. It also goes through these points. So those are the 0th, 1st, and 2nd tangent to the cubic at the point 2. So this is obviously so much fun, you're going to want to do this yourselves. You've already calculated, I hope, the tangents to P at 1 and minus 1, as well as the ones that we've done today. So please construct integer graphs for the tangents to P at 1 and minus 1. So make exact corresponding pictures for the tangents at 1 and also at minus 1. It's very satisfying. And it's calculus. If you want to have something which is a little bit more smooth, you can do a little bit more work, and you can fill in some points by adding some more rational points, maybe at halves. If you want to be more ambitious, you can divide each one up into 4, plot them all, get some nice pictures. Everything can be done by hand. You don't need any artistic ability. Just remember, we're only using line segments to join the dots. So, this is pretty cool, and there's more cool stuff. In fact, we're going to see this cubic again. There's something really remarkable about this cubic, well, in fact, about cubics in general. But to prepare the way for that, I think next time we'll talk about lines and parabolas. The first tangents, tangent lines, are lines. They're pretty easy to understand. Tangent conics are always these parabolas. And we're going to have to know a little bit about parabolas. We'll study them algebraically and draw some pictures. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.